עבודה די קשה, כן? למה דיפ לרנינג עובד? התשובה היא שבעצם רוב הפרמטרים שלך בעצם לא באים לידי ביטוי, הם פרמטרים לא אפקטיביים, ולכן אתה לא יכול לדאוג להם. הם לא יצאים כמו זמן אירון. אפשר לחשוב על זה קצת אחרת. במקום להסתכל על זה ככה ולבזר את החסמת האקספרשן, להסתכל על ה-DKL ולעשות לזה איזשהו גרדיאנט דיפרנס, וכל פעם לבחור את ההתפלגות שהיא תוריד אותו במובן. אתה יכול לעשות את הפרוג'קשן על ידי גרדיאנט דיפרנס. כן, זה בדרך כלל הרבה פחות יעיל. מה שיפה בפרוג'קשן האלה זה שאתה יכול לעשות דברים גדולות. כלומר, אתה תחשוב על ה-EM, כן, הסיפור הראשון למשל, מספיק לך בדרך כלל את המוצרים כבר כדאי חדשים. הסיכונים הבאים הם קטנים אם זה תאי יחסית. ואם תעשה גרדיאנט דיסנט, תתחיל לספור, תיקח לך מאוד איטרציות. זה אונליין אולי. אבל שאלה מצוינת, למה השיטות האלה של פרודקשן יהיו בעוד יותר גרוע? אם אתה נורא תמיד לרנג'ן אמריק, גרדיאנט דיסנט זה סופר עוד אמריק. כלומר, אתה כל פעם עושה צעד קטן מכיוון הגרדיאנט, יכול להתקע מהר מאוד וזה לא תמינו, מה שאתה עושה פה זה דומה יותר לסקנד אורדר, של ניוטון רפסון. אז השיטות של סקנד אורדר, של ניוטון רפסון, מה זה ניוטון רפסון? אתה רוצה לעשות אופטימיזציה, או אתה רוצה למצוא שורש, אתה רוצה לעשות אופטימיזציה, אתה מחליט על המשיק. אתה מחליט על המשיק, אתה חושב את הגרדיאנט, אבל לא דרך קצת. אתה הולך עד הנקודה שהגרדיאנט חוצה את האפס. זה שיטות גדולות מאוד. אלה שיטות של סקנד אורדר, הן בדרך כלל מאוד יעילות כאשר אתה כבר נמצא באזור הנכון. לפחות אזור הפלקידיאמט שאתה נמצא עכשיו. זה לפי מה שקוראים מהם, אם אתה קרוב זה בסדר, אם אתה רחוק זה יכול להיות מאוד בסדר.
Okay, good afternoon. Siwei is not here, but because of the recording, I'll continue in English. So what I want to do today, Hagai, what I want to do today is finish the discussion on grid cells, but we're back to the whiteboard, and then continue from where we stopped last week, which is linear decoding, and I'll hopefully finish that topic as well. So the one thing I want to do today on grid cells is to go over an argument from the paper of Balasubramanian, This is a paper that I mentioned yesterday. So far it appears on the archive, an electronic archive. You can look for it if you want to read it. Actually, I'll put it on the Moodle. I know that it's in review right now. Balasubramanian. I rehearsed it. Vijay Balasubramanian. He's a physicist in New York, working on various topics in neuroscience. So the argument is an optimization argument. It's an argument trying to predict what should be the set of grid spacings from a point of view of decoding. And I think it's a nice argument. It's very simple, as you'll see. At least the version that I will present to you. There are some refinements in the paper which are more complicated. And one of the reasons I think it's very nice is that it was written before this was known. It was written before it was known that grid spacings are a geometric series. And it doesn't only argue for a geometric series, it also gives a reasonable argument why the ratio between subsequent spacings should be of order 1.5. I'll do a 1D version in one dimension, but it can be generalized quite easily to higher dimensions. So what are our assumptions? We assume that, first of all, location is a one-dimensional variable. We assume that we have spacings, grid spacings, that I will denote by lambda I, and I will, following the notation in the paper, I will take lambda 1 to be the largest and lambda m to be the smallest. And I will denote by the resolution of readout from each module, of readout from each module as Li. What do I mean by resolution? Suppose that you observe all the spikes from the neurons in one particular module. So the module has a certain periodicity. This would be lambda I. If you try to infer where the animal is based on the spikes from one module, one thing that is clear, it's going to be periodic, because the neurons in one module cannot tell us whether we're here or here or here. But if there are enough neurons in the module, we will have some readout which might be a little bit fuzzy. Okay? We won't be able to tell exactly where the animal is. There will be some range. And the same thing will be, this will be just periodic, right? Now you can quantify somehow the error. Right? Suppose that the animal is truly, if we have enough cells in the grid cells, this will be localized close to the true position of the animal. Okay? And you can somehow quantify what is the error here. And we talked in the past week or two about ways to estimate error when you to quantify error when you estimate a variable, a continuous variable. But here, let's keep it a little bit fuzzy. We'll not decide exactly how to define it, but I think it's at least qualitatively, it's clear what we mean. Li is the range of this, is the spread of this posterior probability given the spikes. Okay, now one main assumption made in this paper I mentioned this yesterday. No, sorry, this assumption I didn't yet mention, that the number of neurons required to reach a resolution Li for a module with spacing lambda I, is this okay still? No? But this is okay? So the number of neurons required, okay, is Ni which I will call Ni. The assumption is that this is related to lambda I, it's related to Li. And can you guess, I mean, how could it behave? Lambda has dimensions of length. L also has dimensions of length, right? So what is the simplest way to generate a number which is dimensionless? Take the ratio, right? And so this is a very reasonable assumption that the number of neurons is proportional to lambda I divided by Li. It's certainly a function, just on grounds of dimensional analysis, it's certainly a function of this ratio. Yes. So if I would take this module and just stretch the lambdas and stretch the L at the same time, obviously I will need the same number of neurons to achieve these properties, because the scale it has units. It's arbitrary. I can stretch things arbitrarily. So it's certainly a function of this ratio. The assumption here is that it's simply proportional to this ratio, okay? Which is a reasonable assumption. You've seen already that when we discussed Fisher information was typically proportional to the number of neurons. Okay. Third assumption, another assumption, is an assumption on progressive refinement. Yes, beta is some coefficient. So the assumption in the way the argument is spelled out in the paper, it's linear. Okay, that's the assumption.
And the number of neurons is per spacing and module, or?
It's per module. Spacing and module is the same. Module is all the neurons with one spacing. So all the neurons, number of neurons sharing the same. So we assume that
So you have the same number of neurons in each spacing as the number of spacings?
we have, for each module, we have a certain number of neurons, which is Ni. And so far, the assumption is that this number is some constant times the ratio between lambda I and Li.
Yeah, because we have the same I. So it seems lambda I and Li, the I's are the module.
That's right.
The Ni is the scalar number of the neuron inside that.
No. Ni is the number of neurons participating in that module that have that spacing. And we assume that they densely represent all phases within the module. I should have said that. Okay. Now, another assumption is progressive refinement in readout. What this means is that the notion is that the largest module, lambda 1, has a spacing which is compatible with the size of the range, with the range of the representation. So if this would be the whole environment, based on lambda 1, you could tell where you are in the environment. And then they use the second lambda 2 in order to, lambda 2 has a certain periodicity, so you use lambda 2 to decide where you are within this range, and then you use lambda 3 to refine further and further. This assumption tells us something about the relationship between the resolution of the ith model and the spacing of the I-1 module. I mean, what it tells us is that the I+1 module. It tells us that we want this range to be smaller than the spacing of the next module. Okay? So that in the next module, we will not have ambiguity. Suppose that this is the periodicity of the next module. We will know that we are in this period of the next module and not in this one. Okay, but if this would be larger, if the range of the ith module would be wider, we would still have some ambiguity whether we're here or here. So that's another assumption. And the last assumption is that the overall resolution of the readout is the last L. It's the L of the smallest module, so it's Lm. In reality, all this is a little bit too simplified. the resolution of the readout is we can use not only, I mean, here the assumption is that we're using only the smallest module to pin exactly where we are, whereas the spikes coming from the larger modules, from the smaller lambdas, are also informative about this. So this is a bit oversimplified, but if you will look at another paper by Andreas Hertz that I mentioned yesterday that does things more correctly using calculating Fisher information and using assumptions on Poisson spiking, essentially it's buried in the paper. It's not so hard to see it in that paper, but you will see that the overall resolution is proportional to the resolution of the smallest module. Yes, Hagai? No, the notion is that Li, okay, so this is Li. Now imagine that we want to use the next module, and the next module has some periodicity lambda I plus 1. The idea is that this should be smaller than that periodicity so that you will know exactly in which one of the periods you are. No, the next one has a smaller. This is the way I defined it. I'm just following the notation in the paper, so that's why I did it this way. Okay. And what is the goal? The goal is to minimize the total number of neurons. Which is, let's call it n. It's simply sum of ni, I going from 1 to m. What is constrained? In this paper, what is constrained is lambda 1, the largest grid spacing, which is assumed to be really the range of the representation. We talked yesterday about the fact that actually the range of the representation can be much, much larger than lambda 1, but this is not it is ignored in this paper. And constraining the resolution, which, as I said, is assumed to be Lm. Okay. So now let's talk about the optimization principle, about the calculation, what the argument. So let's define, actually I'll do it here, define Ri to be lambda I divided by lambda I plus 1. Why am I looking at the ratio? Because in the end, the conclusion would be that all the Ri's are the same. So let's see how we get to that conclusion. So the next step is that what we say is that in order to minimize the number of neurons, we want to make the resolutions as large as possible for each lambda. Larger resolution means smaller number of, when I mean larger, coarser. Larger Li means coarser resolution, and this will require a smaller number of neurons. So the next assumption is you're going to saturate equation 3. This is it. Okay? So set Li to be exactly equal to lambda I plus 1. So as I said, it's I wouldn't call it an assumption. I would call it a rough estimate of the true resolution of the code. And you can do better than that. You can calculate it. I mean, you will have to throw in additional assumptions about noise because as you've seen in the course, to calculate something like Fisher information, you have to assume something about the statistics of noise. So for example, decide that the neurons are Poisson, as we've done when calculating Fisher information for neural populations last week. So do that and consider all the coding properties. You can estimate the Fisher information. This has been done in another paper by another group. In the end, their conclusion is that if you look at it carefully enough, you realize that the resolution of the code is proportional to the resolution or to the spacing and resolution of the smallest module. Okay, but I'm not. So here it's an assumption. Here it's an assumption. Okay. This is what is assumed in the mathematical derivation that we're following right now. Okay? And the goal is to minimize the number of neurons while fixing the range and the resolution. Okay.
How is R and M defined?
This is just a definition.
No, but Rn would be...
I'll write it in a moment. We'll need it. I didn't yet use it, but when I'll use it, I'll define it. Good question. Okay, so this is another kind of assumption. It's not. I mean, I think it can be proven that this is the best thing to do, but for now, let's just assume that it's the case. That in order to minimize the number of neurons, it's best to make the LIs as large as possible, given the lambda I plus 1s. And if we do that, then we can, this equation, we can also rewrite using the RIs. I'm getting now to your question. So lambda I is then equal to Li times Ri, right? I just replaced lambda I plus 1 sorry, this should be lambda I plus 1 divided by lambda I. No. This is okay. So is this okay what I'm doing? Lambda I plus 1 is, yes, it's lambda I divided by Ri. So I multiply by Ri both sides of the equation, and I get this. And now I want this to be true also for lambda m. But so far I defined Ri for I equals 1 to m minus 1. Right? So just in order for this to be true also for lambda m, I define Rm to be equal to lambda m divided by Lm. Okay? All right. So now let's write lambda 1. Remember that lambda 1 is one of the parameters that we're fixing. This is one of our constraints. So write lambda 1 using these parameters, the L's and the R's, using the R's. So we can write it as lambda 1, R1 times lambda 2, which is R1 times R2 lambda 3, and it's going to be, therefore, in the end equal to R1 times R2 times Rm Lm. Okay? Why am I doing this? I'm doing this because lambda 1 is one of the parameters that we're fixing, and Lm is one of the parameters that we're fixing. So now, lambda 1 divided by Lm, which is, if you want, the dynamic range of the code, it's the ratio between the range and the resolution, is kept fixed. But you see that and we're now writing it in terms of the parameters that we want to optimize, R1 up to Rm. Okay, so now we want to maximize. What do we want to maximize? We want to maximize n, which is the sum of ni, I going from 1 to m. But this I can write as sum beta, sum lambda I over Li. I'm using now this assumption for the number of neurons required in each module. But lambda I divided by Li is Ri. So this is beta, sum let's write it explicitly, beta R1 plus R2 plus Rm. Okay, so what do we need to do? We need to optimize this while fixing this. And before we even try to do it, we observe something very nice. The parameters that we're playing with are the Ri's. But you see that both these properties are completely symmetric in all the Ri's, in permutations of the Ri's. There's no, all of the Ri's appear here in exactly the same way, right? Here it's a sum, here it's a product. So therefore, the optimum, there's no reason why some of the Ri's should be larger than the others. The optimum will be some optimum where all the Ri's are the same. Okay? So without even doing the calculation, we already see from the symmetry here with respect to permutations of the Ri's, the fact that all of them appear in the same way, that the solution will be a fixed R for all the modules, meaning that the spacings are a geometric series. Okay? But now let's do the optimization. Because what I need to optimize is the sum of all the Ri's, and my constraint is on the product of all the Ri's. So there's no, all of them are exactly, appear here in exactly the same way. If you would relabel them, it will still, this expression will look the same. I mean, there's no, right? If I tell you optimize the sum of two numbers given a constraint on the product, the optimum will be one where both of them are the same, because they're equivalent to each other. In fact, it's a bit more complicated, because there could be what we call symmetry breaking. There could be sometimes a solution where it's preferable to make Ri very large, say, and all the other ones 0. But if that's the case, you will also have another solution where you could do it the same for the R2 and R3, but that's not, for this problem, really the solution ends up being a solution where all the Ri's are the same. And such, I mean, there certainly is an optimum of these equations, an optimum of these equations given this constraint because of the symmetry. So that's, I'm doing kind of the short explanation for why they end up being the same. But let's also do the optimization. So given that I assume that all of them are the same, what do I need to do? I need to maximize m times beta times r while fixing r to the m, which needs to be lambda 1 divided by Lm. Okay, so let me take this equation and express m using r. So m log r is equal to log lambda 1 divided by Lm. And now I'm going to plug this here. So m beta r is equal to beta r log, beta log lambda 1 divided by lambda m times r divided by log r. This is n. And now if I want to require that dn to the r is equal to 0, I don't care about all this. This is a prefactor. What do I get? I need to take the derivative of this with respect to 0. So I have log r in the denominator squared, 1 times the derivative of the numerator multiplied by the denominator. So it's 1 times log r minus the numerator times the derivative of the denominator. Derivative of log r is 1 over r, so it's r times 1 over r, so I get here 1, and this is to be 0. Therefore, log r is equal to 1, and I get r equals e. Okay? Which is approximately 2.7. Okay? Now, in 2 dimensions, I would get, I'm not doing it here, but in 2 dimensions it ends up being square root of e, which is about 1.65. 3 dimensions, and there is also an argument in the paper why it should be a triangular lattice. And in 3D, it ends up being square root to the 3 of E. I'm mentioning 3D because maybe grid cells will be observed in 3D in bats, and this is about 1.4. Okay, now one last point that I'd like to make. Yes, yes. So this is.
Why did we end up max?
Sorry. Thanks for noticing this. This should have been min. We want to minimize, and here too. This should have been minimized, and it's indeed a minimum. Okay, I didn't show this, but it's indeed a minimum. Okay. So now one last comment before I proceed is that this looks like an extremely general argument. I'd like to show you how it might become a little bit less general, slightly. Remember that we assume this. We assume that Li is equal exactly to lambda I plus 1. But Li is a statistical property. It's something like the mean error in the estimate of position in a given module. It's not clear that you want exactly equality here in order to be able to read out the code in an unambiguous way. Remember, this is not a requirement that came from resolution. It's a requirement coming from unambiguous readout. We want to be able to read out position from the largest module, then refine it unambiguously in the second module, then refine it again unambiguously in the third module. In order for us to be able to do it statistically, to be able to do it at least most of the time, or maybe always, it's not clear that we need exactly equality here. So just suppose, for the sake of my argument, then that our requirement would be that Li should be proportional to lambda I plus 1, but maybe maybe it has to be even a little bit better than this. Maybe alpha should be smaller than 1. Li should be a bit smaller than lambda I plus 1. If that's what you assume, here you will get something like alpha to the m, because when here we would have an alpha. The alpha will appear in each step. I won't do the calculation, but if you repeat the same calculation that I've done so far, you will get that R should be alpha times E. Okay? So it's not difficult to argue for some slightly smaller spacing than the ratio of spacings than E. And in the paper they discuss this not in this way, but discuss it in a bit more detail. That they find various readout schemes for the position, and claim that in some readout schemes you will indeed get E, but in others you will get something slightly smaller than E. Nevertheless, I think it's a very nice argument both for the scaling argument, the fact that you get a fixed ratio between modules, and it gives a order of magnitude estimate for what we expect the ratio to be, which is in very nice agreement with reality. Okay, there are many more interesting things to say about grid cells, but we need to progress in the other topics. So I'm going back now so I'm finishing this part. Are there any questions about this or more general? Okay, so we'll continue now in discussing linear decoding. Last time I talked a little bit about discrimination. I argued that for Poisson neurons, the maximum likelihood discriminator is a linear operation, can be described as a linear operation performed on the spike counts followed by thresholding. You will continue to discuss this in the TA session. And I started to talk about estimation, and I argued that estimation is not a linear operation. Maximum likelihood estimation cannot be, the maximum likelihood estimator cannot be written as a linear function of the spike counts. Okay? I will not repeat this now, but it's not linear operation in NI. Nevertheless, we can ask what can we do if we want to perform linear estimation, if we want to perform estimation using a linear function. Why? Because a linear function, first of all, is the most simple function that we can think of, and it corresponds to something that we know neurons can do. Neurons can sum up inputs in a linear fashion. So it's interesting to see how would we construct an estimator if we required it to be linear. And much of what I will say now is not restricted to Poisson neurons. As you will see, if our requirement, in the requirements that I will define, we can do the derivation even if the neurons are not Poisson. And when we need the Poisson, as an example of the Poisson, I will say this explicitly. Okay, so my assumption is that we have observations Ri from the different neurons, and there's a parameter theta, so there's some probability of Ri given, of the vector R given theta. This function defines both how the Ri's depend on theta, and it also defines the noise model, because it tells me for a given theta how the Ri's are distributed around their mean and what are the possible answers for the Ri. And now I want to construct a linear estimator which is written as follows. It's a sum of Wi Ri plus some bias. This is the most general linear function that I can write based on the observations. And what is my is my goal? My goal is to minimize the mean square error, which I will write here. E is the average of theta minus the true theta square. Now, when I'm writing an average like this is important to notice when I continue the derivation. I actually mean here two averages. One is the average over the statistics of R given theta. This is the neural noise. But I'm also averaging over the thetas. Okay? So this is an average over R given theta and over theta. In other words, if I want to write explicitly what this is an integral d theta, P of theta. Let's assume that theta is drawn from some distribution. So this is P of theta. And then for each theta, the mean error is an integral over all possible neuron responses, their probability given theta. And now, once I defined both theta and R, this is, I know what, on the other hand, on one hand theta, I also know theta hat, so I can write this difference squared. Theta hat of R minus theta squared. Okay? So this is an explicit representation or expression for what I want to minimize. I'm actually not going to use this expression as it's written here. I'm writing it just to write a very concrete expression for what this quantity is. Now, let's write it using the structure of the linear decoder. So I want to write the average of sum over I, Wi, Ri plus B minus theta squared. Again, the average is both over the neural noise and over theta. But this is simply a square of a linear expression, so let's just explicitly write this square. So I will have various terms. I will have this thing squared, this thing squared, this thing squared, and then all the mixed terms. So let's start with this one. I have here, I will write this as sum over I and j, Wi, Wj. These are numbers, so I don't need to average them. Ri's are random variables, so over Ri, Rj, I need to put the average. Okay, so this is the square of this term, right? I will also have the square of this term, which is b squared. I will have the square of this term, which is theta squared. Now, theta is a random variable, so let's write it this way. And then I have the mixed terms. So I have the mixed term coming from these two terms. This is 2 times b times sum over I, Wi, Ri average. Again, I'm just keeping inside the averages only the quantities which are random variables. Quantities which are not random variables, I'm putting outside the average. There's also a mixed term from this and this. So this is minus b sum over I, Wi. Both Ri and theta are random variables, so I'm putting both of them inside the average. And which term that I didn't yet use? I think this mixed term. And there was a 2. There's a missing 2 here, right? The mixed terms that have a 2 on with them. And there's also here minus 2 times b, average of theta. Okay. It looks a bit complicated, but as you'll see, the end result will be very elegant. So, first of all, now what do I want to do? Yes. Sorry. What? Yes. No, this is from this one and this one. Maybe I put here. Yeah, there's no b. You're right. You're right. Thanks. The b was wrong. Okay, so what are my parameters? My parameters are b and the wi's. So I want to optimize with respect to them. Let's start with b. So this is e, right? So dE to dB has to be 0. What does that tell me? This doesn't depend on b. This gives me 2b. This gives me plus 2 sum over I, Wi, Ri. And here I get minus 2 theta average equals 0, meaning that b is equal to sum over I to theta average, the average of theta, minus sum over I Wi Ri average. Okay. It's some constant. Yeah. The estimator is defined
Why you derive it?
because it's a parameter. I allowed the linear estimator to have any form structure of. Did I erase this? No. This is my estimator, and I decided I'm looking both at b and at wi's as parameters that I'm free to adjust. My parameters, the estimator is parameterized by the weights and b. and I want to choose the best linear estimator that I can find. Okay? Now, I would like to point out that this equation has a nice interpretation. I mean, it can be interpreted a little bit more nicely than just looking at this result, but maybe I'll put it in put a frame around it because it's important. So let's ask what is the average answer that my estimator will give. The average estimate that my estimator will give across many experiments. I draw theta from P of theta. I draw the neural response given theta. I ask my estimator to estimate theta and ask what will it answer on average. So what will it answer on average? It will answer on average W transpose, the weight vector, times R average, right, plus B. This is just the average of this quantity. But now you see what B is. This term exactly cancels this term, so this is equal to the mean of theta. Okay? So this is a consequence of this equation. On average, the answer of my estimator will be the average value of theta. This is a bit similar to what we discussed, to the definition of an unbiased estimator, but note that this does not tell us that this estimator is unbiased. If the estimator would be unbiased, it would mean that for any given value of theta, the average of theta hat given that theta is equal to theta. Here, all this is saying is that on average, the estimator is unbiased. On average, over all possible values of theta, the answer of the estimator will be equal to the average of theta. But it could be that for some thetas, the estimator is biased. In fact, a linear estimator of this form is usually biased. I'm not showing it, but it's usually biased. Okay, what is left to do is that I need to do the derivative with respect to the weights, and this will either happen next week or after consultation with Neta, maybe in the next hour. But now let's take a break. כן, בדיוק. W ו-B זה קבועים. בדיוק. כן, נכון מאוד.
אבל אתה אומר שזה לא unbiased, כי זה כאילו...
כי אני ממצא פה על כל הערכים של תטא. unbiased אומר שאם אני אקח את תטא קבוע ואציג לאסטימטר של הרבה פעמים את ה-R שנובע מאותו תטא, בממוצע הוא יחזיר את אותו תטא. פה יש ממוצע על התטאים.
פה אתה אומר שכאילו לכל ה...
תטא נגזר מאיזה התפלגות, נגיד שתטא עצמו נגזר מאיזה התפלגות שנראית ככה, סתם, לא חייב להיות פרסיאנית, יש לו איזה ערך ממוצע, תטא ממוצע, ואם אני הרבה פעמים אציג אני אבחר תטא מההתפלגות הזאת, אני אציג לאסטימטור שלי את התגובה הנוירונית שבאה מהתטא הזה, אני אבקש ממנו להעריך את תטא, ואני מצא את הדברים האלה, בממוצע אני אקבל את אותו תשובה, זה משהו הרבה יותר חלש.
כן.
הרבה יותר חלש.
ממש בשיעור הזה, פשוט קשר לפיתוח טיילור, פשוט התרגיל הזכיר לי את זה, ואז חשבתי שאני הבנתי שגיליתי שלא הבנתי. אבל לא צריך לזה שהתרגיל, אבל... על הפיתוח טיילור שעשינו לגרסה לוגר, בהקשר של ה-discrimination, שעשינו פיתוח טיילור, וגם לקחנו את הפיתוח והראינו שזה מרתיע. אני רוצה לזה שבאתי בזה, כי ניסיתי לעשות את הפיתוח, ראינו שהממוצע היה ביטוי כזה, לגרסה לוגר, וראינו שהממוצע בא מכאן, וזה יצא שזה מינוס J, כפול זה. וזה היה במקרה שאנחנו תטא שווה תטא אחד, וניסיתי להראות לעצמי שכשנניח תטא 2 אני אקבל את זה מין. אז הבנתי שאו שלא הבנתי מה עשית, או שהבנתי מה עשית, ואז אני לא יודעת איך להגיע את זה עם 2.
אז לכן זה טוב לעשות את זה, כי אז את רואה יש פה איזה קבוע איזה משהו. הנקודה היא קריטית, שאנחנו הנחנו שבעצם פה זה תטא אחת, פה כתוב זה בעצם גיוון תטא אחת, ואנחנו הנחנו שתטא, R נגזר גם מההתפלגות של R גיוון תטא אחת. זה הביטוי לפישר, וזה דברים האלה ביטויים לפישר אינפורמיישן. כי בפישר אינפורמיישן צריך שני דברים, שה-R הוא גיוון תטא אחת פה, ואת כל זה ממצאים על R שמתקבל מאותו תטא.
כאילו אתה מדבר גם על...
גם פה. שהממוצע פה הוא על ה-R'ים, הממוצע פה על ה-R'ים שנגזרים לתטא אחת גם כן. עכשיו, אם הייתי...
אחרת זה כאילו היה פישר אינפורמיישן.
לא, רק לא, זה אפס. שראינו שזה אפס, השתמשנו בזה, זה אותו תטא אחת פה, וה-R נגזר מאותו תטא אחת. אם היית מניחה שפה כתוב תטא אחת, וה-R נגזר מתטא שתיים, הדבר הזה כבר לא היה אפס. היה אצלנו משהו עם סימן הפוך שהוא קשור גם לפישר אינפורמיישן. זה מה שצריך קצת לחשוב. אז זה לא היה אפס בכלל. אז היה פה איזשהו איבר שהוא מתאר בריבוע, כל פה דלתה תטא.
אבל היה ממש שזה אפס בגלל התכונה של הלא פשוט, לא בגלל...
אבל זה בגלל שפה... לא,
כאילו,
אחרי שממצאים על פי... אחרי שממצאים על פי של R גיוון תטא אחת...
כאילו, אם אתה אומר זה אדם, אם היה פישר שתיים, זה לא היה אפס.
ואז היה מתקבל משהו שהוא ניסן פרופורציוני לדלתה תטא, אוקיי? פרופורציוני לדלתה תטא, ואז כל הדבר היה נותן משהו יותר דלתה תטא בריבוע, כמו האחד הזה. אי אפשר היה להתעלם מזה.
אוקיי, אז אני רוצה כן לעבור את זה, כי מה שאני צריך לפתוח, פיתוח טיילור לפי תטא שתיים.
אז צריך לעשות כאילו פיתוח טיילור של הפי של הדלתה יותר קלה, אני חושב, ולקחת את הפי שפה מופיע בעצם שהוכחת שזה אפס. כאן עכשיו מופיע R של תטא שתיים. עכשיו תכתבי את פי של R גיוון תטא שתיים בתור פי של R גיוון תטא אחת, פלוס דלתה תטא כפול פי. תחשבי פי של R גיוון תטא אחת, פי של R גיוון תטא שתיים יש סיכון. אז תקבלי, אז האיבר שהוא פי של R גיוון תטא שתיים,
אבל מה אתה כאילו זה לא דלתה תטא?
הוא קשור לנגזרת של פי של R לפי תטא. ואז מה יקרה? כשפה יש תטא שתיים, פה יש תטא שתיים, כשפה יש את הדלתה תטא, דיפי לוי תטא, פה יש דיפי לוי תטא, זה בסוף יוצא הפי של R.
אז כאילו, אז אתה אומר לא לשנות את הפיתוח הזה, אלא כשאני עושה את הממוצע, לשנות את הביטוי.
כן, ואז תקבלי פה, שהוא גם כן מסדר דלתה תטא בריבוע, והוא בדיוק יהפוך את הסימן.
אני לא בטוחה, אבל איך אני עושה, כאילו, שאני עושה שם דלתה. אם אני עושה, אתה אומר לי לשון את זה. אני רוצה להתייחס? ואני אגב לא נשאלת להתייחס. יש השוואה לאחר.
שטויות, השוואה לאחר.
כאן.
מה שאני אומר, תביא את פי של R שזה גיוון תטא אחת, פי של R גיוון תטא שתיים.
זהו, אני לא מבינה איך.
פיתוח טיילור, כמו שעשינו כזה, ועוד דלתה תטא, כפול פי של... דיפי לדי תטא.
כמו פיתוח טיילור שעשינו.
כן. אז תראי שבעצם מה שיקרה באורח קסם זה מה שתראי באורח קסם זה איפה היינו? לא, זה שהאיבר הזה יצא מינוס משהו, אני יודע דלתה תטא בריבוע, בדיוק יהפוך את הסימן. במקום לקבל פה חצי דלתה תטא בריבוע, פה J תקבלי מינוס.
זהו, אז אוקיי, אז קיבלתי, אז משהו אולי עשיתי נכון, קיבלתי את זה, בלי להביא את מה שאמרת, עשיתי פשוט פיתוח, אולי בעצם עשיתי אותו דבר, כאילו עשיתי, כשהגעת לכאן, לדלתה לוג L, אז גם פיתחת את פי של R בהינתן תטא 2 כפונקציה, כאילו עם טיילור של פי של R בהינתן תטא 1, אז אני עשיתי הפוך. פיתחתי את פי של R בהינתן, עשיתי פשוט טיילור הפוך, שזה לא אמור
טוב, לא יודע, אני צריך לראות מה עשית כדי להגיד אם אני מסכים שזה נכון.
לא, זה לא נשמע לי נכון, שאם אני אפתח את תטא 2, אז
לא,
קיבלתי את זה במינוס. קיבלתי את זה במינוס.
יפה, זה גם נכון.
אבל למה זה נכון? לא הבנתי למה זה נכון, למה זה משנה מול... למה זה שאני פתחת את תטא 2 אומר משהו על מי התטא האמיתי?
דלתה לוג L באמת, אם את נמצאת על תטא אחת הוא חיובי, ואם את נמצאת על תטא 2 הוא שלילי, אז זה הגיוני, זאת אומרת, אין שום דבר. טוב, אנחנו צריכים לדבר על זה, תחשבי על זה, זה כן הגיוני. הדרך יותר קלה לקבל את הסימן מינוס היא לראות, לפתח סביב תטא 2.
זה בול משהו, זה בפועל.
אז יצא מינוס.
אבל לא הבנתי למה.
אז הנה, עכשיו אנחנו בדרך אחרת, למה?
לא, הדרך שאתה הסברת על זה.
זה הגיוני, מה זה הדלתה לוג L? דלתה לוג L זה הלוג הסתברות של תטא 2, פחות לוג הסתברות של תטא 1. אם הספייקים נגזרים מתטא 2, הגיוני שזה יהיה חיובי. אם הספייקים נגזרים מתטא 1, הגיוני שזה יהיה חיובי.
לא, זה נכון, אבל למה הפיתוח טיילור שלי מעיד על מי התטא האמיתי?
לא, כי מה שחשוב זה סביב מי את מפתחת. זה קריטי שפה, כשעשיתי את זה בדרך האחרת, אז שוב פעם פה הופיע גם R2 כאן וגם R2
אני לא חשבתי על הממוצע, פשוט...
זה הנקודה.
הנקודה היא הממוצע לדעתי, על מי הממוצע, מי ההתפלגות שאנחנו
היכולת לאפס את האיבר הזה היא רק כאשר...
בגלל זה יצא לי, פשוט לא שמתי לב, לא באמת הבנתי למה זה יצא לי אפס. סבבה, תודה.
אוקיי.
רק קודם כל, אתה רוצה לגנוב לי 5 דקות?
זה קצת תלוי פשוט מה מצבך, מה אתה מעריך.
כאילו, לשם שינוי, זה עושה שמחה את
פשוט אני קצת מרגיש שאני תקוע באמצע
אז אני אכניס לו עכשיו.
אני צריך רגע להסתכל.
וגם מתן ביקש לי לקחת 2 דקות כדי להודיע להם על איזה פרויקט של אפס.
כן, אוקיי, זה קצת יותר מ2 דקות. אני אקח בשביל 10 דקות. לא, אפילו תדעת מה שיש לך הוא לא שלושת ראשון שיש בו איזה חלקים משהו שאני יכולה לבטל עליו. אני אתן לך לעשות את התרגיל.
אוקיי, ויש לי עוד 2 דברים קטנים. קודם כל לגבי הלמה שאני אמרה לי שאני אמרה לדרך הכי חשובה להגיד את זה. רק שיש בגלל שאני שניהם קוונטונים, נשארים קוונטונים שצריכים אותם. וקוונטון שהלם לי של אותו סוף הוא גאוסיאן.
זה היה המנהיג שלי.
יש לנו תחום של שניהם קוונטונים. אולי עוד משהו. אני לא חושב, אין לי עוד דרך סגורה להגיד את זה.
תראי, בגדול עוד פעם, כל המשפט הגבול המרכזי הוא נובע מזה שהלוג ההסתברות יש לו איזה מקסימום, ליד המקסימום הוא פרבולה. והמקסימום זה ככל שמוסיפים, אם זה משתנים באותו, אם זה משתנים באותה התפלגות, אז ככל שברור שככל שיש יותר משתנים, אז זה פשוט מוכפל בפקטור. מה שחשוב זה שברור שיש לנו סימון כאלה. זה הסימון.
למה הוא שלום טוב האמת הוא וואו, אני אמרה לי למייסת.
יש לי הרבה נוירונים קודם כל, אם אני מוסיף עוד מאוד נוירונים, הנוירונים שבכלל לא מגיבים לסטימולוס לא רלוונטי. אבל אני מצטרף יותר ויותר את הנוירונים, ויש יותר נוירונים שמגיבים. פשוט מה שקורה זה זה כאילו, הלוג לייקליות היה יותר גדול. המקסימום היה, הלוג לייקליות זה פשוט נהיה פרבולה יותר ויותר גדולה, אבל כשעושים לזה אקספוננציאציה, זה יוצא גאוסיאן, זה בסוף יוצא גאוסיאן. התרומה היא, מה שחשוב, התרומה נהיית משמעותית, היא אזור יותר ויותר צר סביב המקסימום, כי זה דורך להפך, זה אקספוננט של משהו, ואז זה כבר יותר ויותר נכון לחשוב על סיבוב טיילור סביב המקסימום.
לא, ועוד אחד זה ברעיון כן, אנחנו עושים פיתוח טיילור לפוחד ולא לשונות. עכשיו ברור שלשנייה זה לשונות
בדיוק.
אבל אין לי עדיין
אוקיי, אז אני רציתי הנימוק שלי, חשבתי על זה קצת אוקיי, אז אמרנו שמבחינת התוחלת יש לנו התפלגות אחת כזו והתפלגות אחרת כזו, זה קריטי שהתוחלת היא שונה. עכשיו בוא נניח שהשונות הייתה שונה, התוחלת הייתה אותו דבר, אז היה לנו מצב כזה. זה לא חייב להציב עדיין לא היינו יכולים לעשות את זה. זאת אומרת שבסדר מוביל העובדה אם השונות אם התוחלת היא אותו דבר, אז שינוי בשונות לא תורם בכלל ולכן העובדה שיש הבדל בשונות היא תתרום, אבל היא כבר סדר יותר גבוה. כי בסדר מוביל, עוד פעם, אם התוחלת לא הייתה משתנה, זה לא היה עוזר לו. זה פחות או יותר... טוב. כן. אבל נטע, אני לא רוצה לצאת, אז את לא...
פה אתה בעיקרון אמור לעשות מדינה שנייה, לראות שהיא חיובית ולכן זה מינימום, נכון? כאילו, עכשיו, אני לא ממש מבין מה תפסתי, זה אני מסכים, זה פשוט זה. מה אומר עכשיו השוויון הזה?
לא, אני בסך הכל שואל, נגיד שאני אציג לאסטימטר שלי הרבה פעמים את התטא, את הפעילות העצבית, כשתטא נגזר מההתפלגות המקורית של תטא. מה תהיה בממוצע התשובה שלו?
אתה מה חיפשת בי שעושה מינימום לדבר הזה.
זאת התשובה שקיבלתי. עכשיו אני אעזוב רגע את המשוואה. אני שואל, פשוט, סתם אני שואל, אני רוצה לחשב, מהו תטא הט ממוצע? מה זאת אומרת תטא הט ממוצע? אני חוזר לניסוי הרבה פעמים, תטא מעוגל מההתפלגות של תטא, הנוירונים מעוגלים מה-R גיוון תטא, האסטימטור
איך מצאת את זה?
בממוצע מה האסטימטור יעשה? לקחתי את המשוואה הזאת, וזה מה שעשיתי לה. עכשיו השתמשתי בזה כשהצבתי פה את ה-B הזה. אז כשאני מציג את ה-B הזה אני מקבל תטא, פחות זה וזה בדיוק זה.
ועכשיו עוד שאלה, מקודם שעשית אופטימום, הנקודה היחידה שאני לא מבין, למה אתה אומר שאופטימום RI כולם אותו דבר?
כי גם האילוץ וגם הגודל שאני רוצה לעשות אותו לאופטימיזציה הוא סימטרי ולהחלפה של ה-R.
יש לך פה סכום על מלא של R'ים, ואתה רוצה לראות מתי זה מינימלי.
כן.
אז איפה האילוץ?
האילוץ הוא פה, שהמכפלה שלהם היא משהו שגם...
צריך להראות את זה כאילו, אבל...
כן, צריך להראות את זה. אבל זה הגיוני שקיבלתי תשובה שכל ה-R'ים הם זהים, כי אין פה שום הבדל, כל ה-R'ים מופיעים פה בדיוק באותה צורה.
בצד שני לא מופיע. מה, הנוט שלך?
חגי, אני רק אגיד לך את התשובה שלנו, מה שדיברנו אתמול.
זה לא?
כן, זה פשוט קשור לזה שכשמנתחים ואנחנו רוצים להגיד שמשהו של HA, או שאתם מבינים משהו זה, מיעוטים בסוף של המסגרות
So hi guys, we'll just take 2 minutes of your time. So my name is Matan. I'm a student here in ESSEC, and I want to tell you about the project that we are going to launch in the very near future. So the project is called Head Start, and the idea is to go to junior high school students, חטיבות ביניים, and have an introductory lecture or activity about the brain. So the idea is that the people that are going to give these lectures are students or researchers here in ESSEC, and it will be like around an hour or an hour and a half for each class. And the people that are going to give these lectures, they are going to participate in 1 or 2 lectures, so it's really not a burden on the participants. So we are going to prepare a slideshow and activity and to guide you how to do it, and then you can modify it as you like. And then the people that are going to participate, so first of all I think that you get to do something important in your life other than doing research here. You get to try your sorry? Yes.
When it starts?
Sorry?
When it starts?
So it's going to start in the near future, probably in a few weeks. We're going to announce it also to all the ESSEC members and other members that are related to brain, but I think that you fit the most because you are in the 2nd year, right? So you know enough by this time about the brain, and it's still very fresh, and you still have the time to do it, and it's really not a big burden, as I said. So I will just give you my details, okay, and my email, and whoever wants to participate, you are welcome to send me an email, and we will meet and see what we can do. minutes will stay until the end of the class?
2 minutes is the
Okay, thank you.
Okay, so we'll start. The subject of the lesson today is a linear discriminator. So first of all, I will define what is the linear discriminator, what do we mean by linear discriminator. Then we will give some motivation, why is it interesting to talk about a linear discriminator. And then we will do a specific example and find the optimal linear discriminator for a specific case. Okay, so the definition of the linear discriminator is that we have two possibilities that can be either theta 1 or theta 2, and we decide theta 1 if h is larger than some threshold, where h is a linear summation of the spy count, and b is a threshold. Okay, so this is the definition of the linear discriminator. So why is it interesting to talk about this kind of discriminator? So what is the optimal discriminator in the general case? Johan talked about this in class. Not necessarily linear, the optimal discriminator is the ML when the priors of theta 1 and theta 2 are equal. Okay, when it is not equal, it will be the Bayesian estimator, but in all the examples that we talked about them, we assume equal priors, so it was the ML discriminator. But the problem is that sometimes the ML discriminator is not something that is easy to calculate mathematically. Sometimes, like, for example, last week we saw in the second example that it's not so easy to apply the ML discrimination. And the linear discrimination is something that we assume that maybe a neuron can do it, right? It's just a linear summation of the spy count that they can, we can think about postsynaptic neuron that does a linear summation of the spikes of presynaptic neuron with some weight. And if this summation is larger than a threshold b, the neuron will respond. So it's something that we assume that maybe neural networks can apply. So this is the motivation why we want to talk about this kind of discrimination. So sometimes it will be interesting for us to find the optimal linear discriminator. So the linear discriminator that achieves the least probability of error. I will define what we mean by optimality. Okay, so now we will do an example. We will find the optimal linear discriminator for a population of Poisson neurons, as we always do. So linear so we'll assume that NI, the spy count of the neuron I, has a Poisson distribution with parameters that depend on the stimulus, theta. And we'll assume that theta 2 is equal to theta 1 plus a small plus delta theta, where delta theta is small. It will help us when so we want to find the optimal linear discriminator for population of control neurons when we need to decide between theta 1 and theta 2, and we assume that the interval between them is small. Okay, this is what we want to do. So, what do we mean by optimal? So the optimal it minimizes the error E, where E so how do you think we should define the optimality in this case? What will be optimal? What is the best discriminator? Yeah, so the probability for error will be minimized, right? So what is the probability of error? We define it as E, so error. So what is the probability of error? How can we write it? So it's P of theta 1. The probability that the true parameter is theta 1, but the discriminator says that we should choose theta 2, right? But still H is larger than the threshold. Okay, we choose theta 1 when H is smaller than the threshold. So this is the probability of error given theta 1. And we have also...
Depends how we define at the beginning.
Yeah, but at the beginning, no, I think it's okay. No, yeah, sorry. It should be like this. Okay, this is the full way like next step. Okay, so and we also have the probability of error given theta 2, P of H smaller than B given theta 2. Okay, so this is the probability of error, and we want to find W star and V star that minimize this expression. Okay, is it clear until now? The problem? Okay.
But don't we have the same files?
Yes.
So
Yeah, so we will assume that we have the same file. So we assume that P of theta 1 is equal to P of theta 2. It makes everything much more simple. Okay, so now H is the linear summation of the spike counts. This is a random variable, right? For each observation, H will be a random variable, and we need to find and we want to find the distribution of H. Okay, in order to calculate this expression, first we want to find the distribution of H. Okay, so what will be the distribution of H? What do you think? Can you guess? We want to do it before we start. What do you think is going to be? Gaussian. And you don't have my notes, right? Okay, so H is sum over I, Wi, and I, and we claim that the distribution of H is a Gaussian, and Y. So we say that the spike count has a Poisson distribution, and we know two things. So I think that there are more than one way to explain why H is a Gaussian, and I chose one way that makes sense to me. So H and I are Poisson, so also H has a Poisson distribution because some over Poisson variables also have the Poisson distribution, okay? And the second and the other thing that we know is that if the Poisson parameter goes to infinity, the Poisson distribution becomes Gaussian distribution, okay? So these two facts, so sum over Poisson random variable is Poisson, and also if lambda is the Poisson parameter goes to infinity, the Poisson distribution becomes Gaussian. Okay, so using these two facts, we can assume that in the limit of large n, H has a Gaussian distribution. Okay, so now in order to find the distribution, what do we need to calculate? For Gaussian, in order to obtain the mean and the variance, right? This is what we need. So we calculate the mean and the variance of H given theta 1 and theta 2.
This lambda,
Lambda, this is like general property where lambda
the
is
effective lambda of
yeah,
all
the effective lambda of all of these, yes.
Is it equivalent to using the central limit theorem, which is sum of independent
Yeah,
variables?
they are independent variables, but they are not IID. So this n comes from different distributions. So I'm not sure. Maybe there is a way also to use the central limit theorem here, but I'm not sure about this. I know that for the case of IID.
So, but do you still know what the mean and the variance are?
Yeah, we can calculate it. We just know. Okay. Okay. So. Okay, so first of all, the mean of H given theta 1, what is it going to be? It's easy. The mean of this, what is it? You have to know it. What is the expectation value of the summation of random variables? It's sum over all the expectation value of each one of them. Okay, so the expectation value of H given theta 1 is just sum over I, Wi, Fi of theta 1. Okay, Fi of theta is the Poisson parameter, which is the expectation value of each of the n. And the variance, we will mark it as mu1. And what is the variance? Theta 1. What will be the variance? If we know that these variables are independent, so what is the variance of sum over independent variables? It's the sum of the variances, and we need to take the Wi to the power of 2. So it will be sum over I, Wi to the power of 2, Fi theta 1. And we call it sigma 1. Okay? Until now, and similarly, we can calculate these two expressions given theta 2. Okay, so H given theta 2 is sum over I, Wi, Fi of theta 2. And now we'll do remember that theta 2 is theta 1 plus small delta theta. Okay, so what we can do here, we can make a Taylor expansion of this term. Okay, אתם מכירים שאתם נרדמתם? התעורר. בטח. Okay, so this is sum over I, Wi.
But Nessa,
מה?
if you want to minimize the probability of error, bias.
Mm-hmm.
Why you do it again
The probability of error,
so theta 2, you have the mean value theta 1.
because you write that it
You
is.
can write twice.
I still need to justify that it's the same error.
The same are only if fi is independent of theta, no? If fi is different, then
Yeah,
it's
so
different.
it will in this case we'll assume that we'll the next step we'll assume that the two distribution have the same variance, and then will be the same. Okay, so this is the first order expansion, and the variance okay, now doing something else. Maybe it will look strange for you. So here we developed up to the first order. And here we take only the zero order. Okay, so here we did an approximation to the expectation value of H given theta 2, and we took the first order of F, and here we did an approximation to the variance, and actually we say that the variance of H given theta 2 is the same as the variance of H given theta 1. We took only the zero order approximation. So why here we took the first order and here the zero order? So here we cannot take only the zero order, because then we get that H has the same mean given the two in the two situations, and it will not enable us to differentiate between them, but it's possible to show that that this approximation does not change much the probability of error. What?
But then the variance is the same. Why the
Yeah,
mean
the variance
is
is the
okay?
same.
It's not
Because
okay.
I will plot the two distributions. Okay, so now
But Neta,
no,
if you take the first order also for the variance,
you
won't
can do
be,
it.
you'll get square terms, and then the delta theta would get squared, no? No, actually.
No. The W should be zero. Sorry. Yes. Taking over. Okay, so this is a P of H. Okay, and so we have two Gaussians. One of them, this will be mu1, and this is mu2. So it's clear that if I cannot say that these two Gaussians have the same expectation value, right? If this is P of H given 2. But we will assume now that the variance of these two Gaussians is the same, and it's possible also to show it in the mathematically that the probability of error will not change much if we take also the first order approximation in the variance, but we will not do it now. So for now you just need to believe me that it's okay to assume that these two Gaussians have the same variance. Okay, we can talk about it later for those that do still feel uncomfortable with this assumption. So how can I see here? This is given a specific W, this will be the expectation values, but we still need to choose the optimal threshold B. Okay, so where do you Yeah, only because we have equal powers. Yes. Okay, so for a given expectation values, I need to since it's easy to convince yourself that the optimal threshold should be here. Any other way, any other threshold only increase the probability of error. What is the probability of error now? How can I see? How can I see here now the probability of error? With integral this one, right? And this one also. Okay, so now assume that I move that I will move the threshold a little bit to the right. This integral will be larger in any if I move it a little bit here. Maybe I gain a little bit here, but I lose more here. Okay, I think that it's okay. Like for everybody, it's okay. So
Is it okay to say that the two halves are equal of the...
yes, they are equal because the variance is the same. Yeah. Okay, so V star intuitively we show that V star should be here. If some of you feel uncomfortable with that, you can talk to me later. So V star is the average of mu1 and mu2. It's also possible to get it more rigorously, but I think that it's mutar. Okay, so this is V star, and note that still V star is a function of our weight, okay? Because the expectation value is a function of W. So up to now we know V star only as a function of the weight, okay? So the next step is to find the optimal weight, and then just go down. So V star is the optimal threshold, okay? In order to find the optimal discriminator, we need to find the optimal W and the optimal threshold. Okay, we have two things that we need to choose. So let's move it forward. Okay, so now because we have equal priors and we assume that the variance is the same, the minimizing E, the probability of error, is actually as minimizing just one of them, as Chagay said before. So we want okay, so now W star will be the W that's minimizing the probability of error given theta 1. So actually it's only the right part of this integral, okay, because these two parts are equal. Given the threshold V star that we choose for this specific threshold, these two parts of the integral are equal to each other, and then we can just calculate the integral of the right side, which is the probability of error given theta 1. Okay, is it clear? Okay, so what is this expression? How can I write more precisely this expression? What is this? This is the integral over there, the red integral. Integral of what? Yeah, so we say that we assume that H given theta 1. So this is, we assume that 8 has a Gaussian distribution, okay? So we need to do integral of the Gaussian, the integral of the left Gaussian, and we calculate the integral of this Gaussian. We start from B star until infinity, okay? So the lower bound of the integral will be B star. Okay, so we're doing integral between B star to infinity, dh prime, over square root of 2 pi sigma 1 to the power of 2. This is, I'm just writing here the integral of over a Gaussian distribution.
This W, it's not given, base.
It's not, no. So we know B star as a function of W. So for any W, B star will be here in the middle, and the average is the expectation value, but we still don't know what are these expectation value. Everything is as a function of W. So we know B as a function of W, but we don't know what is W. So we want to minimize this expression, and I can also write it, I can do a change of variables. We define y to be h prime minus mu 1 over sigma 1. And then we can write this integral as integral from b tilde. Now b tilde is something else because we did the change of variable, 1 over square root of 2 pi exponent of minus y to the power of 2 over 2 dy. Okay, so now we have an integral over a standard Gaussian from b tilde, which is now, because we did a change of variables, so we also need to change the bound of the integral, right? So b tilde, the new lower bound, is now, I'm substituting like b star. B star is the average of the expectation value, and we already probability of error, we're maximizing this term b tilde. Okay, so actually here you can see on the graph what is b tilde. So b tilde is actually this half of this distance divided by the standard deviation. Okay, so it makes sense that we want the ratio between this, the distance between the peaks, and the standard deviation of each one of the Gaussian to be as larger as possible, so we can do the discrimination better. Okay, so it's possible to see that b tilde is S over sigma, where S is just mu2 minus mu1, half of this distance, over sigma. Okay, if you substitute everything, you can see that this is exactly the b tilde that we have here. So also this term is quite meaningful if we look at it here. Other questions? No? Okay. So now I want to maximize this term.
Sigma square, no?
No, here b tilde is no. This is the square root of sigma square here. It's not sigma square. Okay. So we'll do it here. So b tilde should be larger than 0. So we know that in the for the optimal W, for W star, we know that b tilde should be larger than 0. Why? Because if b tilde is negative, then this integral will be larger than 1 over 2, right? Larger than half. And it doesn't make, so it means that it's worse than just to do the discrimination randomly, right? If we do the discrimination randomly, it means that the probability of error is half. So b tilde should be have to be positive, so the probability of error will be better than just a chance, right? So we assume, so we know that when we will find the optimal W and we calculate b tilde, it will be larger than 0. So why this is important? Because we can just maximize b tilde square, which is much easier mathematically because we don't have the square root here. Okay, so instead of maximizing b tilde, we're maximizing b tilde square. Why?
Why, yes. What's the proof that you can maximize the square?
Because we know that in the optimal solution, b tilde should be positive. Have to be positive. So we can maximize b tilde to the power of 2. So we'll make the derivation of actually the gradient of b tilde square in respect to W.
Bigger or equal? You don't know.
Bigger or equal? Yes, but it's enough. But equal is still okay. Okay, so we make the derivative of this in respect to W. It's just to b tilde square actually. It's just mathematics, but נגזרת של מנה. So we get delta theta to the power of 2, 2 sum over I, Wi, Fi prime of theta 1, Fj prime of theta 1 over for sum over I, Wi to the power of 2, Fi of theta 1, minus d theta to the power of 2. Sum is just a derivative, it's nothing interesting. Wi, Fi prime of theta 1 to the power of 2 over 4 sum wj f j of theta 1. And this should be equal to 0 in the maximum. Okay? So we just need to solve this equation. And since, so we can cancel, no, not this, but this with this, and also this with this, and this, and the d theta. So at the end, you can see that I will still come. That's why before. Okay, so we get that fj prime of theta 1 is equal to sum over I wi fi prime theta 1 over 2 sum over I wi to the power of 2 fi of theta 1 wj fj of theta 1. Okay, so now note that this is actually a scalar. So it does not depend of j. Okay, this is and thus when we write the solution for wj, wj star is f prime j of theta 1 over fj of theta 1 multiplied by a constant. Okay, so this term is the same for all the different components of j. Okay, so I can just write it as a constant. So we got that